Welcome back to the OEIS Deep Dive. We are digging into another fascinating integer sequence today, one that's particularly relevant for you, number theory enthusiasts out there. A000137, the series parallel numbers.
Yeah, it's a sequence with some really interesting connections to another one we've explored before, A000084, which deals with series parallel networks.
Right, so for anyone just tuning into our OEIS journey, we're exploring the online encyclopedia of integer sequences. It's a treasure trove of mathematical patterns.
Yeah, and today's sequence, A000137, starts like this: 1, 2, 6, 18, 58, 186, and so on. These numbers represent the different ways you can construct series parallel graphs with a given number of edges.
Now, you might be thinking, graphs, isn't this about number theory?
Right.
But that's the beauty of the OEIS. It reveals these surprising connections between seemingly different areas of math.
Yeah, series parallel graphs are used in circuit design, but they also pop up in computer science for designing algorithms and analyzing their complexity.
And here's where it gets really intriguing. A lot of problems that are notoriously difficult to solve for general graphs, we're talking NP-complete problems, become much more manageable when you're dealing with series parallel graphs.
Yeah, that's because their structure lends itself to a divide and conquer approach. You can break down a large series parallel graph into smaller subgraphs, solve the problem for those smaller parts, and then efficiently combine those solutions to get the answer for the entire graph.
So instead of trying to tackle a complex problem head-on, you're strategically breaking it down into simpler pieces.
Exactly. This is a key principle behind a powerful technique called dynamic programming, which is often used to solve problems on series parallel graphs.
Now, I remember learning about NP completeness in my algorithms class, but could you give us a quick refresher?
Sure, NP-complete problems are a class of problems for which no one has yet found an efficient algorithm that works for all cases. They tend to become exponentially harder to solve as the input size grows.
So finding an efficient solution for an NP-complete problem, even for a specific type of graph, is a pretty big deal.
Absolutely. And series parallel graphs offer that advantage because of their recursive structure. You can build them up from simple building blocks using two basic operations: series composition and parallel composition.
So it's almost like constructing a sentence. You start with individual words, combine them into phrases, then clauses, and eventually you have a complete sentence.
That's a great analogy, and just like a sentence has a grammatical structure, series parallel graphs have this recursive structure that makes them much more amenable to algorithmic analysis.
And this inherent structure is what allows us to apply techniques like dynamic programming and solve certain problems much faster than we could on arbitrary graphs.
Precisely. And this brings us back to the sequence A000137. The fact that these numbers grow relatively quickly tells us something about the increasing complexity of these networks as the number of edges grows.
It's like the sequence itself is hinting at the intricate world of series parallel graphs and the challenges they pose as they get larger.
And speaking of intricate connections, let's delve into that relationship between A00000084. The formula for the generating function of A000137 directly incorporates the generating function of A000084.
Now, before we get lost in the world of generating functions, could you give us a quick intuitive explanation of what they are and why they're important in this context?
Certainly. Imagine a function where the coefficient of each x to the n term gives us the nth term of our sequence. That's the basic idea behind a generating function. They provide a powerful way to encode the information of an entire sequence into a single function.
So instead of just looking at a list of numbers, we have this mathematical object that encapsulates the entire sequence and allows us to manipulate it in powerful ways.
Exactly. And in this case, the generating function for A000137 is given by x times the quantity 1 plus s, all divided by the quantity 1 minus s, where s is the generating function for A000084.
So the very structure of this formula is highlighting a deep mathematical link between these two seemingly different concepts of series parallel networks and the number of ways to construct them.
Yeah, this connection is fascinating because it allows us to leverage knowledge about one sequence to gain insights into the other. It's like having two different windows into the same intricate mathematical landscape.
And for number theory students like ourselves, it's a great reminder that seemingly abstract concepts can have tangible connections to real-world applications and other areas of math.
It also underscores the power of the OEIS as a tool for discovery. Who would have guessed that a sequence about series parallel graphs would have such a direct link to a sequence about series parallel networks?
It's a testament to the interconnected nature of mathematics. But before we get too carried away with the beauty of it all, Let's get back to that generating function formula. What can it tell us about A000137?
Well, for one, it provides a way to calculate the aimed series parallel number without having to go through the process of constructing all possible series parallel graphs with n edges.
So it's like a shortcut to finding those numbers. Instead of drawing out all the graphs and counting them, we can use this formula to directly compute the answer.
Exactly. And beyond that, the formula can also reveal information about the growth rate of the sequence and other properties. It allows us to analyze the sequence from a more analytical perspective.
That's really insightful. So this seemingly simple formula is packed with information about the behavior of A000137. It's like a mathematical Rosetta Stone for understanding the sequence.
That's a great way to put it. And as we continue our exploration of the OEIS, we'll see time and again how these seemingly abstract formulas can unlock a deeper understanding of the sequences they represent.
Well, I'm definitely hooked. This whole world of series parallel graphs and generating functions is much more fascinating than I initially imagined.
I'm glad to hear that. And just wait until we delve even deeper into the connections between A00000084. There's a whole rabbit hole of mathematical insights waiting to be discovered.
So we've got this powerful tool, the generating function, and this intriguing connection between A000137 and A000084. Where do we go from here?
Well, one path we can take is to explore the implications of this connection for solving problems on series parallel graphs. Remember, we talked about how their recursive structure makes them well-suited for dynamic programming.
Right, the idea of breaking down a problem into smaller subproblems and building up the solution from there.
Exactly. Let's consider a concrete example. Finding the maximum independent set in a series parallel graph. You might recall that an independent set is a set of nodes where no two nodes are adjacent.
And the maximum independent set is the largest possible set of this kind within the graph. Sounds like a tricky problem to solve for a general graph.
It is, but for a series parallel graph, we can leverage its recursive structure. Let's say we have two smaller series parallel graphs, G1 and G2, and we know the maximum independent sets for each of them.
So we've already solved the problem for those smaller pieces.
Now, if we combine G1 and G2 in series, the maximum independent set of the combined graph is simply the larger of the two individual maximum independent sets. We can see this because no node in G1 is adjacent to any node in G2.
That makes sense. We're essentially picking the best solution from the two subproblems.
And if we combine G1 and G2 in parallel, the maximum independent set of the combined graph is the union of the maximum independent sets of G1 and G2.
Because in a parallel composition, every node in G1 is adjacent to every node in G2, so we can't include nodes from both in our independent set.
Precisely. So by exploiting the recursive structure of series parallel graphs, we can break down the problem of finding the maximum independent set into these smaller, easily solvable subproblems.
And this is where dynamic programming comes in. We can store the solutions to the subproblems and reuse them as we build up to the solution for the entire graph.
That's right. This approach allows us to solve the maximum independent set problem, which is generally NP-complete in linear time for series parallel graphs.
That's a huge improvement in efficiency. So by understanding the structural properties of series parallel graphs and using techniques like dynamic programming, we can overcome computational challenges that would be insurmountable for general graphs.
Exactly. And this is just one example of how the insights we gain from A000137 and its connection to A000137 can lead to practical solutions in areas like algorithm design.
It's really fascinating to see how these abstract number sequences can have such tangible implications for real-world problems.
And it highlights the importance of exploring these connections between different areas of mathematics. Who knows what other surprising applications might be hidden within the depths of the OEIS?
It's like a treasure hunt for mathematical insights. But speaking of the OEIS, we've been focusing a lot on the computational aspects of series parallel graphs. What about their combinatorial properties? What else can A000137 tell us about the structure of these graphs?
Well, the sequence itself can provide valuable information about the growth rate of the number of series parallel graphs as the number of edges increases. The fact that the numbers in A000137 grow relatively quickly suggests that the number of possible series parallel graph configurations explodes as we add more edges.
So the complexity of these graphs increases rapidly with the number of edges, which is reflected in the sequence itself.
And this growth rate can be further analyzed using the generating function. By studying the properties of the generating function, we can gain a deeper understanding of the asymptotic behavior of the sequence, meaning how it behaves as the number of edges tends towards infinity.
That's pretty advanced stuff, but it sounds like the generating function is more than just a tool for calculation. It's a powerful lens for examining the underlying structure and behavior of the sequence.
Precisely. And as we delve deeper into the world of generating functions and their applications, we'll uncover even more fascinating insights into the properties of integer sequences like A000137.
It's amazing how much information is packed into these seemingly simple mathematical objects. It makes you wonder what other secrets are hidden within the vast expanse of the OEIS.
There are countless mathematical treasures waiting to be discovered. And the beauty of it all is that each discovery opens up new avenues for exploration, leading us down paths we could never have anticipated.
It feels like we've only just scratched the surface of A000137 and its connection to series parallel graphs.
Yeah, and that's the beauty of the OEIS. Every sequence is a doorway to a whole world of mathematical exploration.
So for our listeners who are ready to dive deeper, where would you recommend they go from here?
Well, the OEIS entry for A000137 itself is a great starting point. It lists references to research papers and other resources that delve deeper into the properties and applications of series parallel numbers.
It's like a curated bibliography for anyone who wants to go down this particular rabbit hole.
Exactly. And beyond that, I'd encourage listeners to explore the world of generating functions more broadly. There are some excellent textbooks and online resources that explain the theory and applications of generating functions in a clear and accessible way.
That sounds like a great next step for anyone who wants to develop a deeper understanding of how these mathematical tools can be used to analyze integer sequences.
And of course, the OEIS itself is an endless source of inspiration. Just browsing through the entries can lead to unexpected discoveries and spark new avenues of mathematical inquiry.
So as we wrap up our deep dive into A000137, what's the key takeaway you'd like our listeners to remember?
I think the most important message is that even seemingly abstract number sequences like this one can have deep connections to real-world problems and other areas of mathematics.
It's a reminder that math is not just a collection of isolated facts and formulas, but rather a beautifully interconnected web of ideas.
And by exploring the OEIS and delving into sequences like A000137, we can gain a deeper appreciation for the beauty, power, and surprising relevance of mathematics.
Well said. Thanks for joining us on this fascinating journey into the world of series parallel numbers. We hope our listeners will continue exploring the OEIS and uncovering their own mathematical treasures.
It's been a pleasure. Until next time, happy exploring.